What if everything you see around you, the stars, the planets, even the air you breathe, isn't quite as solid or separate as it appears? Picture this for a moment. The universe isn't just a collection of objects floating in empty space, but a dynamic, ever-shifting tapestry where matter and energy are locked in an inseparable embrace. This isn't just poetic imagery, it's the very foundation of reality itself. From the smallest particles to the vast expanses of galaxies, the dance between matter and energy shapes everything we know, and yet, so much of this cosmic choreography remains hidden from plain sight. Today, we're pulling back the curtain on one of the universe's most profound mysteries, the intricate, interwoven realities of matter and energy in space. Think about the last time you watched a sunset, the way light bends and scatters, painting the sky in fiery hues. That breathtaking display isn't just light interacting with air. It's a glimpse into the deeper relationship between energy and the fabric of our world. Matter isn't just a passive participant in the universe. It's constantly exchanging energy, transforming, and even bending the rules of space-time itself. Stars aren't just burning balls of gas. They're colossal factories where matter and energy collide, creating the elements that make up everything from the mountains to the cells in your body. Black holes aren't just cosmic vacuums. They're extreme laboratories where the very boundaries between matter and energy blur into something almost unimaginable. This journey isn't just about understanding the universe, it's about redefining how we see our place within it. By the time we're done, you'll never look at the night sky the same way again. We'll explore how energy shapes matter, how matter warps the fabric of space, and how this eternal dance gives rise to the cosmos as we know it. From the quantum realm to the edges of the observable universe, we're about to uncover the hidden connections that bind everything together. So if you've ever wondered what truly lies beneath the surface of reality, or how the universe manages to balance such incredible forces with such precision, stick around. What you're about to discover might just change the way you see everything. To grasp just how deeply matter and energy are entwined, let's start with something you've likely heard of but may not fully appreciate, that iconic equation, E equals mc squared. At first glance, it might seem like just another scientific formula, but this simple arrangement of letters holds the key to understanding the universe's most fundamental exchange. Energy isn't just something matter has, it's something matter can become, and vice versa. Picture a star like our sun, where every second millions of tons of matter aren't just burning, they're transforming directly into energy through nuclear fusion, lighting up the solar system. Or consider something far smaller, a particle and its antiparticle colliding in a flash of gamma rays, their mass vanishing into pure energy in an instant. This isn't just theoretical, it's happening right now all around us. Take a simple matchstick. When you strike it, the chemical energy stored in its molecules converts into heat and light. But here's the cosmic twist. That energy didn't just appear. It was always there, locked within the matter itself, waiting to be unleashed. Now scale that up to a supernova, where a dying star's core collapses, and in a heartbeat, matter becomes an unimaginable burst of energy, outshining entire galaxies for weeks. That's the universe's grand alchemy at work, yet the dance goes deeper. Even in the seeming emptiness of space, energy and matter are in constant conversation. Quantum fields buzz with particles flickering in and out of existence, borrowing energy from the vacuum itself, a proof that nothingness is anything but empty. And then there's dark matter, that mysterious substance weaving through galaxies, invisible yet shaping them with its gravity. We can't see it, can't touch it, but its presence screams that our understanding of matter and energy is still incomplete. What's truly astonishing is how this interplay creates the conditions for life. The carbon in your bones, the oxygen in your lungs, they were forged in stellar furnaces where matter and energy reached a perfect balance, allowing atoms to assemble into the complexity that makes you possible. So when you look up at the night sky, remember, you're not just a spectator to this cosmic symphony, you're part of its melody, born from the same eternal exchange that lit the first stars. If stars had a recipe, it would read something like this. Take enormous clouds of hydrogen gas, sprinkle in gravity's relentless pull, and wait as pressure builds to unimaginable levels. But this isn't just a cosmic cooking show, it's the moment matter and energy become indistinguishable. Deep within stellar nurseries, those vast, glowing clouds of dust and gas, atoms don't just bump into each other. They're crushed so violently that their very nuclei fuse, transforming hydrogen into helium in a process that releases staggering amounts of energy. This isn't mere combustion, it's matter rewriting its own rules. Every photon of sunlight that warms your skin began as a single proton surrendering its identity to become pure energy. Consider the Orion Nebula, one of the most active star factories visible from Earth. Within its swirling tendrils, newborn stars ignite like matches in the dark, their brilliance powered by the same atomic alchemy that fuels our sun. But here's what's even more remarkable. The weight of a star directly dictates its destiny. A modest star like ours will burn steadily for billions of years, its gravity and radiation locked in a graceful equilibrium. But a massive star, it lives fast and dies young, its core raging like a pressure cooker until it can no longer hold back the tide. When such a star exhausts its fuel, it doesn't just fade, it collapses inward, then explodes outward in a supernova so powerful that for weeks it outshines entire galaxies. In that cataclysm, matter doesn't merely vanish. It becomes the energy that forges heavier elements: carbon, oxygen, gold, scattering them across space to one day become part of planets, oceans, even living things. Yet the dance doesn't end there. Some stars are so dense, so massive, that when they die, they don't just explode, they collapse into neutron stars, where a teaspoon of matter weighs as much as a mountain. Others become black holes, regions where gravity warps spacetime so severely that not even light can escape. These aren't just cosmic oddities, they're extreme examples of how matter and energy can bend, twist, and transform under conditions we're still struggling to comprehend. What's truly humbling is realizing we're made from the aftermath of these stellar explosions. The iron in your blood, the calcium in your bones, they were forged in the hearts of long-dead stars, then hurled across the universe by supernova. When you gaze at the stars, you're not just looking at distant suns. You're seeing the factories that built the very elements of life itself, where matter and energy perform their endless, intricate dance. Black holes aren't just cosmic vacuum cleaners, they're the universe's most extreme laboratories, where the rules of matter and energy are rewritten in ways that defy common sense. Picture this, a place so dense that a single teaspoon of its core would weigh billions of tons, where gravity isn't just strong but unbreakable, warping space and time into a one-way street. At the edge of a black hole, the event horizon marks the point of no return. Cross it, and not even light, the fastest thing in the universe, can escape. But here's the paradox. While black holes consume matter and energy with unmatched ferocity, they also radiate energy in ways we're only beginning to understand. Take Hawking radiation, for example. In the seemingly empty space around a black hole, particle-antiparticle pairs flicker in and out of existence, a quantum quirk normally harmless. But at the event horizon, one particle might fall in while the other escapes, stealing a tiny bit of the black hole's energy. Over eons, this slow leak could cause even the mightiest black hole to evaporate. That's right, a cosmic giant that devours stars might one day vanish in a whisper of particles, turning its mass back into pure energy. Then there's the mind-bending way black holes warp time itself. Imagine watching a clock fall toward a black hole. As it nears the event horizon, time would appear to slow down. From your perspective, the clock's hands would crawl to a stop, frozen in the final moment before crossing the threshold. Yet for the clock itself, time would pass normally, plunging into oblivion. This isn't science fiction. It's Einstein's theory of relativity in action, proving that matter and energy don't just shape space, they twist time into knots. But the real mystery lies inside. At the center of a black hole, matter is crushed into a singularity, a point of infinite density where our laws of physics simply break down. Is it a gateway to another universe, a knot of pure energy? We don't know. What we do know is that black holes are anything but simple voids. They're cosmic transformers, taking matter and energy and pushing them to limits we can't yet fathom. And every discovery, from gravitational waves rippling from their collisions to the glowing rings of light around their shadows, hints that the answers might rewrite physics itself. So the next time you hear about a black hole, remember, it's not just a dark pit in space. It's a frontier where matter and energy dance on the edge of the impossible, challenging us to think deeper about the fabric of reality. And somewhere in that darkness, the universe might be hiding its greatest secrets. We like to think we understand the universe, that the stars, planets, and galaxies we see make up the bulk of what's out there. But here's the unsettling truth. Everything we can observe, from the smallest atom to the largest galaxy cluster, accounts for less than 5% of the cosmos. The rest, a cosmic mystery in two parts: dark matter and dark energy. These invisible forces don't just exist alongside ordinary matter, they dominate the universe, pulling and pushing in ways that defy easy explanation. Start with dark matter, the universe's hidden scaffolding. Imagine a spiderweb, nearly invisible until dew droplets cling to its threads, revealing its intricate structure. That's how dark matter works. We can't see it directly, but its gravitational grip shapes everything we can see. Galaxies spin so fast that, by all rights, they should fling themselves apart, yet something unseen holds them together. Galaxy clusters behave as if they contain far more mass than their visible stars and gas suggest. Even light bends around empty patches of space, warped by the gravity of something we can't detect. Dark matter isn't just a placeholder for our ignorance. It's a tangible, if elusive, part of the cosmic dance, a silent partner guiding the motion of stars and galaxies. Then there's dark energy, the universe's most baffling force. Unlike gravity, which pulls things together, dark energy pushes space itself apart, and it's winning. In the late 1990s, astronomers made a shocking discovery. The expansion of the universe isn't slowing down as expected, but accelerating. Something dark energy is stretching the fabric of spacetime faster and faster, as if the cosmos is inflating against its own will. Picture a balloon with invisible hands tugging at its surface, forcing it to grow larger even when you stop blowing air into it. That's dark energy's handiwork. What makes these forces so perplexing is how they oppose each other. Dark matter's gravity tries to knit the universe together, while dark energy tears it apart. Their tug of war dictates the fate of everything. Without dark matter, galaxies would never have formed. Without dark energy, the universe might have collapsed in on itself long ago. Yet for all their influence, we still don't know what they are. Are they particles, fields, something entirely beyond our current physics? Here's the humbling part. We're like ants trying to understand the ocean by studying ripples in a puddle. Every observation, the way galaxies move, the way light bends, the way the universe expands, hints at a reality far stranger than we've imagined. And somewhere in that mystery lies the next great leap in our understanding of matter, energy, and the cosmos itself. Imagine two coins spinning in perfect unison but separated by the width of the universe. No matter how far apart they travel, flipping one instantly determines the state of the other, not through some hidden signal, but through a connection so profound it baffled even Einstein, who famously called it spooky action at a distance. This is quantum entanglement, the universe's most intimate dance between matter and energy, where particles become so deeply linked that their fates are intertwined across space and time. At the heart of this phenomenon lies a truth stranger than fiction. When particles like electrons or photons become entangled, measuring one immediately affects its partner, no matter the distance. Picture two dice rolling simultaneously on opposite sides of the galaxy, yet always landing on matching numbers. This isn't magic, it's the quantum world obeying rules that defy our everyday intuition. What's even more astonishing is that this connection isn't carried by any known force or particle. It's as if the universe maintains a secret ledger, updating the state of entangled particles faster than the speed of light, violating classical physics' most sacred speed limit. But here's where it gets even weirder. Entanglement blurs the line between matter and energy entirely. Take a pair of entangled photons. They're massless particles of pure energy, yet their behavior is dictated by the same quantum rules that govern electrons, which have mass. This suggests that at the deepest level, the universe doesn't care whether something is matter or energy. It's all part of the same interconnected web. Scientists have tested this phenomenon in groundbreaking experiments, sending entangled particles miles apart and confirming their instant connection. In 2017, Chinese researchers even used a satellite to beam entangled photons to ground stations over 700 miles apart, and the correlation held. These aren't just lab curiosities, they hint at a reality where separation might be an illusion, and the fabric of space-time is far more flexible than we thought. What does this mean for the cosmic dance of matter and energy? Entanglement suggests that the universe operates like a vast, invisible network, where every particle state is somehow linked to others in ways we're only beginning to decode. Some theories propose that black holes or even the Big Bang itself might have left behind entangled particles scattered across the cosmos, weaving a hidden tapestry of connection. Others speculate that entanglement could be the key to quantum computers, teleportation, or unlocking the true nature of spacetime. One thing's certain, this spooky connection forces us to rethink what matter and energy truly are. If particles can influence each other instantaneously across cosmic distances, then the universe isn't just a collection of separate objects, it's a symphony where every note is played in perfect, mysterious harmony. And somewhere in that entanglement lies a clue to the deeper unity of all things. The story of the universe begins not with a whisper, but with a roar, a cosmic explosion so violent it makes every supernova look like a spark in comparison. We call it the Big Bang, but that name doesn't quite capture the sheer, incomprehensible scale of what happened. Picture this, all the energy and matter that would one day become galaxies, stars, planets, even you compressed into a space smaller than a single atom. Then, in less time than it takes to blink, that infinitesimal point erupted, expanding faster than the speed of light itself. In that first fraction of a second, the universe wasn't just born, It was forged in a firestorm of pure energy, setting the stage for everything that would follow. For the first few moments, the cosmos was too hot and dense for even atoms to exist. Particles like quarks and electrons zipped through a searing plasma, constantly colliding and transforming. Then, as the universe cooled, something miraculous happened. Energy began to crystallize into matter. Protons and neutrons assembled like cosmic Lego bricks, forming the first hydrogen and helium nuclei. This wasn't just random chaos, it was the universe's first delicate balancing act, where matter and energy found equilibrium just long enough to lay the groundwork for structure. By the time the universe was 380,000 years old, it had cooled enough for electrons to finally latch onto those nuclei, creating the first true atoms. Light, which had been trapped in the swirling plasma, suddenly broke free, a flash now visible as the cosmic microwave background, the oldest photo in existence. But the dance was far from over. Over millions of years, gravity began pulling those hydrogen atoms together into vast clouds, which collapsed under their own weight to ignite the first stars. Their brilliant light re-ionized the universe, energizing the cosmos a second time and setting the stage for galaxies to form. Here's the astonishing part: every element heavier than helium, the carbon in your cells, the oxygen you breathe, the iron in your blood, wasn't made in the Big Bang. It was cooked up later in stellar furnaces and scattered across space by supernova. The Big Bang gave us the raw ingredients, but stars became the universe's alchemists, transforming simple atoms into the complexity that makes life possible. Even now, 13.8 billion years later, we're still riding the shockwave of that initial explosion. The galaxies racing away from us, the leftover heat of creation glowing faintly in deep space. It's all part of the same unfolding story. So when you look up at the night sky, remember, you're not just seeing distant points of light, you're witnessing the echoes of that first transformative moment, when energy and matter began their eternal dance, a dance that's still shaping the cosmos today. And somewhere in that grand performance, the universe found a way to turn stardust into storytellers. Neutron stars are what happens when the universe decides to play by its own rules, squeezing an entire star's worth of matter into a sphere no wider than a city. Imagine taking the sun with its colossal mass and crushing it down until it could fit inside Manhattan. The result: an object so dense that a single sugar cube's worth of its material would outweigh Mount Everest. This isn't just extreme physics, it's matter pushed to the brink of impossibility, where atoms surrender entirely, and protons and electrons fuse into a sea of neutrons. But neutron stars aren't just bizarre cosmic paperweights. Some of them spin at dizzying speeds, rotating hundreds of times per second, so fast their surfaces move at a fraction of light speed. These are pulsars, nature's precision lighthouses, beaming radiation across the cosmos with such regularity that their pulses rival atomic clocks. When astronomers first detected these signals in the 1960s, they nicknamed them LGM for Little Green Men, mistaking their perfect rhythm for artificial transmissions. The truth was even stranger: a spinning neutron star, its magnetic field funneling energy into narrow beams like a cosmic strobe light. Then there are magnetars, neutron stars with magnetic fields so intense they'd erase your credit cards from thousands of miles away. A magnetar's field is a quadrillion times stronger than Earth's, capable of twisting the very fabric of atoms. In 2004, one such star halfway across the galaxy unleashed a burst of energy so powerful it briefly outshone the full moon, despite being 50,000 light-years away. That flash wasn't just light, it was the star's crust cracking under magnetic strain, a stellar earthquake radiating gamma rays across the cosmos. What makes these objects so fascinating isn't just their extremes, but what they reveal about matter itself. Inside a neutron star, conditions are so intense that neutrons might dissolve into a soup of quarks, or even stranger states physicists call strange matter. Some theories suggest their cores might contain portals to other dimensions, or bubbles of pure energy suspended in spacetime. We can't recreate these conditions in any lab. Neutron stars are the lab, testing the limits of quantum mechanics and relativity in ways no experiment ever could. Yet even these cosmic oddities have a poetic side. When two neutron stars collide, the explosion doesn't just send shockwaves through space, it forges gold, platinum, and other heavy elements in a kilonova blast. The wedding ring on your finger, the circuitry in your phone, they might owe their existence to such a cataclysm billions of years ago. So while neutron stars might seem like distant curiosities, they're also reminders. The universe's most violent events are often the ones that make life possible. Antimatter sounds like science fiction, but it's as real as the screen you're staring at right now, just far more elusive. Picture a perfect twin to every particle in the universe, identical in every way except with opposite charge. Electrons have positrons, protons have antiprotons, even quarks have antiquarks. These aren't just theoretical curiosities. They've been created in labs, trapped in magnetic fields, and even used in medical imaging. But here's the cosmic riddle. If matter and antimatter are perfect mirror images, why is the universe filled with stars, planets, and people instead of just light? When matter and antimatter meet, they don't just vanish, they transform into pure energy, obeying Einstein's famous equation with explosive precision. A single gram of antimatter annihilating with matter would release energy equivalent to a small nuclear bomb. This symmetry is so precise that physicists expected the Big Bang to have created equal amounts of both, leaving the universe with nothing but radiation after their mutual destruction. Yet here we are in a cosmos dominated by matter, with antimatter so rare it has to be painstakingly manufactured particle by particle. So where did all the antimatter go? One theory suggests that during the universe's first microseconds, a tiny asymmetry, perhaps one extra matter particle for every billion matter-antimatter pairs, allowed a remnant to survive annihilation. Experiments at CERN Large Hadron Collider are hunting for even the slightest difference in how matter and antimatter behave, searching for clues in the decay patterns of exotic particles. Another possibility, antimatter might be hiding in plain sight, trapped in vast clouds between galaxies, or even forming entire anti-stars we haven't yet detected. The stakes couldn't be higher. Solving this mystery wouldn't just rewrite physics textbooks, it would explain why anything exists at all. Every atom in your body, every photon from the sun, every distant galaxy is here because at some critical moment, the universe tipped the scales in favor of matter. And until we understand how, one of the most fundamental questions, why there's something rather than nothing, remains wide open. What's tantalizing is how close we've come to catching nature in the act. In 2021, researchers measured a subtle discrepancy in the magnetic properties of protons and antiprotons, a faint hint that the mirror might not be perfectly aligned. Meanwhile, experiments with antihydrogen atoms, antimatter's answer to hydrogen, are testing whether antimatter falls up instead of down in gravity's grip. Each discovery, each dead end, brings us closer to unraveling a puzzle that's been 13.8 billion years in the making. So the next time you look at your reflection, remember, the universe might have preferred a version of you made of antimatter. That it didn't is one of physics' greatest unsolved mysteries, and the reason you're here to ponder it at all. Imagine a universe where nothing has weight, where electrons zip around at light speed, unable to slow down enough to form atoms, where stars and planets never coalesce because gravity has nothing to grip. This isn't some far-fetched thought experiment, it's exactly what reality would look like without the Higgs field, an invisible energy tapestry stretching through every corner of space. Think of it like an unseen cosmic molasses, subtly resisting particles as they move, giving them the property we call mass. Without this resistance, the universe would be nothing but frenetic, formless energy, a dance without dancers. The story of how we uncovered this field reads like scientific detective work. Back in the 1960s, physicists Peter Higgs and others proposed a radical idea. What if particles aren't inherently heavy? What if their mass comes from interacting with an omnipresent field? It took nearly 50 years and the most powerful machine ever built, the Large Hadron Collider, to confirm it. In 2012, scientists announced they'd found the Higgs boson, a fleeting particle that's like a fingerprint proving the field's existence. This wasn't just another discovery, it was the final piece in the puzzle explaining why matter has substance at all. But here's where it gets fascinating. Not all particles interact with the Higgs field equally. Photons, the particles of light, zip through it untouched. That's why they're massless and move at the universe's speed limit. Electrons, on the other hand, wade through just enough to give them a tiny bit of heft, allowing them to orbit atomic nuclei. Quarks, the building blocks of protons and neutrons, slog through the field like swimmers in thick syrup, acquiring most of the mass in everyday objects. This delicate variation is why the universe has structure, why atoms can form, why chemistry exists, why you can stand on solid ground instead of passing through it like a ghost. The Higgs field doesn't just explain mass, it reveals how deeply intertwined energy and matter truly are. When particles gain mass, they're essentially borrowing energy from the field, converting it into something tangible. It's as if the universe has an infinite credit line and particles are withdrawing just enough to become real. Even more mind-bending, the Higgs field's strength isn't arbitrary. If it were slightly weaker, atoms would fly apart, slightly stronger, and stars might never ignite. This perfect tuning hints at something profound. The laws of physics aren't just random rules. They're a finely balanced recipe, and the Higgs field is the secret ingredient that lets matter and life exist at all. So the next time you pick up a book or feel the weight of your own body, remember, you're not just interacting with gravity or molecules. You're feeling the whisper of an invisible field that turned energy into substance, chaos into cosmos. Without it, the universe would be a featureless void, no stars, no planets, no dancers in the grand ballet of existence. With it, the stage was set for everything. Time isn't the constant we imagine. It's more like a river flowing at different speeds depending on the energy surrounding it. Einstein's theory of relativity shattered the idea of a universal clock, revealing that time bends and stretches in the presence of massive energy. Picture two identical clocks, one placed on Earth's surface, the other launched into space aboard a satellite. Over months, the space clock ticks slightly faster, not because it's faulty, but because Earth's gravity, a curvature in spacetime caused by its mass, slows time itself near its surface. This isn't science fiction. It's the reality GPS satellites account for daily, adjusting their signals to keep your phone's maps accurate. Now amplify this effect to extremes. Near a black hole where gravity is so intense that light struggles to escape, time doesn't just slow, it nearly grinds to a halt. From a safe distance, you'd watch an astronaut falling toward the event horizon appear to freeze in place, their movement stretching into infinity. Yet for the astronaut, time passes normally, a paradox that reveals spacetime isn't just a stage for matter and energy, it's an active participant in their dance. This phenomenon, called gravitational time dilation, shows that energy doesn't merely exist within time, it sculpts time's very flow. But gravity isn't the only force that warps time. Velocity does too. Imagine a spacecraft accelerating to near light speed. As its kinetic energy skyrockets, time onboard slows relative to Earth. At 99% light speed, a 5-year journey for the crew might span decades back home. This isn't just theoretical particles called muons, created when cosmic rays hit Earth's atmosphere, should decay before reaching the surface. Yet because they move so fast, their internal clocks slow enough for many to survive the trip. Time dilation isn't a quirk, it's a fundamental feature of the universe, proving that energy and spacetime are threads in the same cosmic fabric. What's truly mind-bending is how this intertwines with matter. Every object with mass carries potential energy thanks to E equals mc squared, meaning even a humble rock subtly warps time around it. In a neutron star's crushing gravity, atomic nuclei are squeezed so tightly that time passes 30% slower than on Earth. Scale this up to the early universe, where energy densities were so extreme that a single second near the Big Bang might equate to billions of years today. Time itself was malleable, stretching and compressing as energy transformed into matter and back again. This temporal dance has practical consequences. Colliding black holes don't just ripple space, they vibrate time, sending gravitational waves that stretch and compress the duration between ticks of distant clocks. Even Earth's rotation, by dragging spacetime around it, creates frame-dragging effects measurable by precision satellites. The deeper we look, the clearer it becomes. Time isn't separate from the cosmic ballet of matter and energy, it's the rhythm they move to. And somewhere in that rhythm lies the key to understanding how the universe keeps time on scales from the quantum to the cosmic. Every second, as you read these words, thousands of high-energy particles are piercing through your body, not from some local source, but from explosions so distant their light hasn't even reached us yet. These are cosmic rays, atomic fragments racing across the universe at nearly the speed of light, carrying within them the fingerprints of supernova, colliding neutron stars, and perhaps even more exotic cataclysms we've yet to discover. Unlike the gentle starlight we see with our eyes, cosmic rays are brute messengers, packing enough energy to make the most powerful particle accelerators on Earth seem quaint by comparison. Take the "oh my god" particle detected in 1991 over Utah. This single proton, smaller than an atom, hit Earth's atmosphere with the kinetic energy of a baseball pitched at 60 miles per hour. But here's the catch. It was moving so close to light speed that relativity amplified its punch to levels that defy intuition. Where did it come from? Even now, decades later, we're still piecing together the cosmic crime scene. The leading suspects include active galactic nuclei, where supermassive black holes fling matter outward in jets stretching millions of light years, or perhaps dark matter factories, hypothetical regions where invisible particles annihilate in bursts of detectable energy. What makes cosmic rays so valuable is how they bridge the gap between matter and energy in ways light alone can't. When these particles collide with Earth's atmosphere, they shatter into cascades of secondary particles, a natural laboratory for physicists studying how energy converts into matter on scales we can't replicate. Some of these collisions even produce antimatter, offering fleeting glimpses into the universe's preference for matter over its shadowy twin. Yet their journey here is half the story. Cosmic rays don't travel in straight lines. They're deflected by magnetic fields threading through galaxies, turning space into a labyrinth where the particles' paths twist and turn. By the time they reach us, their origins are scrambled like a cosmic game of telephone. That's why observatories like the Pierre Auger Array in Argentina don't just detect the particles. They track the faint blue glow of their atmospheric collisions, working backward to triangulate possible sources. The deeper mystery: some ultra-high-energy cosmic rays appear to arrive from voids, vast, empty regions of space where no known astrophysical powerhouses reside. This has led to wild but tantalizing theories. Defects in spacetime left over from the Big Bang, cosmic strings vibrating with primordial energy, or even collisions between parallel universes leaking energy into our own. Whatever their source, each particle is a bullet fired from the universe's most violent frontiers, and decoding their secrets might rewrite our understanding of how matter and energy dance at the extremes. So the next time you feel a random shiver or sense an unexplained burst of energy, remember, it might just be the universe sending a message written in particles, delivered at light speed, and waiting for us to decipher its code. At the heart of our solar system burns a cosmic furnace so reliable we often take it for granted: the sun, a seething sphere of plasma where matter transforms into pure energy on a scale that dwarfs all human invention. Every second, deep within its core, 600 million tons of hydrogen nuclei collide with such force that they fuse into helium, releasing energy equivalent to billions of nuclear bombs. This isn't just raw power, it's a precisely tuned alchemy that's kept Earth bathed in warmth for 4.6 billion years, turning a lifeless rock into a thriving planet. The magic lies in quantum tunneling, a process where protons overcome their natural repulsion like ghostly intruders passing through walls. Normally, positively charged hydrogen nuclei would never get close enough to fuse. Their electric fields push them apart with immense force. But the sun's core, at 15 million degrees Celsius and under pressures 250 billion times Earth's surface, creates conditions where particles move so fast and squeeze so tightly that quantum uncertainty takes over. Protons don't just collide, they teleport past each other's defenses, merging in a chain reaction that powers the star. Yet this engine doesn't burn like a wildfire. It's a slow, rhythmic pulse, a balance so delicate that gravity's crushing inward pull is perfectly countered by the outward pressure of fusion's energy. If the sun burned too fast, it would exhaust its fuel in a cosmic blink. Too slow, and life might never have gained a foothold. Instead, it's been radiating with near-constant brightness for eons, converting 4 million tons of mass into energy every second through Einstein's E=mc². That energy, born as gamma rays, takes 100,000 years to zigzag through the sun's dense layers, transforming into visible light by the time it reaches the surface. What's often overlooked is how this process built the very atoms we're made of. The helium forged in the sun's core is just the beginning. In older stars, heavier elements like carbon and oxygen form through successive fusion stages, each requiring higher temperatures and pressures. Our sun isn't massive enough to create those elements itself, but it's the keeper of a legacy, recycling material from long-dead stars that once lit the night skies of a younger universe. Every photon that touches your skin is a thread in that ancient story, a whisper of stellar ancestry written in light. And here's the cosmic irony: the sun's brilliance is also its mortality. In about 5 billion years, when its core hydrogen depletes, this steady fusion will falter. The star will swell into a red giant, its outer layers engulfing Mercury and Venus, possibly even Earth, before shedding them into a glowing nebula. Yet even in death, it won't truly vanish. The carbon, oxygen, and stardust it leaves behind will one day seed new stars, new planets, perhaps new life. The dance that began in its core will continue elsewhere because the universe never wastes a single spark. So when you feel sunlight on your face, remember, you're not just soaking up warmth. You're witnessing the grandest recycling program in existence, where matter becomes energy becomes matter again, in an endless loop that connects us to everything the cosmos has ever been. Gravity isn't just a force, it's a language, and the universe speaks it through ripples in the very fabric of reality. When two black holes, each weighing tens of times the mass of our sun, spiral toward each other in a final, violent embrace, they don't just collide, they send tremors through spacetime itself. These distortions, called gravitational waves, aren't made of matter or light. They're pure energy, stretching and compressing space as they race outward at the speed of light, carrying secrets of the most cataclysmic events in the cosmos. Until recently, we were deaf to this cosmic symphony. But now, thanks to instruments like LIGO and Virgo, we've learned to listen. Picture spacetime as a vast, still pond. Drop a pebble into it, and concentric waves spread outward. Now imagine that pebble is a black hole merger with the energy of 1,000 supernova. The waves it produces aren't water. They're distortions in the dimensions we inhabit, squeezing Earth ever so slightly as they pass. In 2015, LIGO detected its first gravitational wave, a signal from two black holes merging 1.3 billion light-years away. The event lasted just 0.2 of a second, but in that heartbeat, the detectors measured a shift in their arms smaller than 1/10,000th the width of a proton. That's like measuring the distance to Alpha Centauri, the closest star system, with an accuracy of one human hair. What makes these waves revolutionary isn't just their existence, it's what they reveal. Light can be blocked, scattered, or absorbed, but gravitational waves pass through everything. They're the ultimate cosmic messengers, bringing us unfiltered news from the darkest corners of reality. When neutron stars collided in 2017, the event wasn't just heard as gravitational waves. It was seen in gamma rays, X-rays, and even visible light, marking the dawn of multi-messenger astronomy. For the first time, we witnessed gold and platinum being forged in real time, validating theories about the origins of heavy elements, but the real magic lies in the details. Each gravitational wave carries a fingerprint of its source, the masses of the colliding objects, their spin rates, even the environment around them. Some waves sound like chirps, others like thuds or rumbles. By analyzing these signals, we've discovered black holes of sizes we never predicted, found hints of exotic objects like boson stars, and even tested Einstein's theory of relativity in extreme conditions. There's a whole universe of collisions out there, black holes merging with neutron stars, supermassive black holes devouring stars, even the faint echoes of the Big Bang itself waiting to be heard. This isn't just about observing the cosmos differently, it's about rewriting our place in it. For centuries, astronomy relied on light. Now, we've gained a new sense, one that lets us perceive the invisible choreography of matter and energy in ways our eyes never could. And somewhere in those ripples, the universe might be whispering its greatest secrets about the nature of gravity, the birth of black holes, or even the possibility of hidden dimensions. The era of gravitational wave astronomy has just begun, and the soundtrack of the cosmos is more astonishing than we ever imagined. What if our universe isn't the only version of reality? What if there are countless others, each with its own unique rules governing how matter and energy interact, some where gravity is stronger, others where light moves slower, or even realms where atoms never formed at all? This is the Multiverse Hypothesis, a concept that stretches the limits of our imagination and challenges everything we think we know about existence. Take inflation theory, one of the leading ideas in cosmology. It suggests that in the first moments after the Big Bang, space-time expanded exponentially, creating vast bubble universes isolated from one another. Each bubble could have different physical constants, perhaps one where the strength of electromagnetism makes stars burn blue instead of yellow, or another where dark energy's repulsive force is so weak that galaxies never drifted apart. In some of these universes, matter might clump so densely that black holes dominate. In others, energy could be so evenly distributed that no structures form at all. The variations aren't just theoretical, they're mathematical inevitabilities if inflation is true. Then there's the quantum multiverse, where every possible outcome of every event spawns a new reality. In this version, there's a universe where you turned left instead of right this morning, one where dinosaurs never went extinct, and even one where matter and energy never decoupled after the Big Bang, leaving the cosmos a featureless sea of plasma. These branches aren't science fiction, they're implied by the equations of quantum mechanics, where particles exist in superpositions until observed. If the math holds, reality isn't a single thread but an endlessly splitting tapestry. But the most mind-bending possibility, universes with entirely different dimensions. Ours has 3 of space and 1 of time, but string theory suggests there could be realms with 4, 6, or even 10 spatial dimensions. In a 4-dimensional universe, gravity might follow an inverse cube law instead of an inverse square one, making planetary orbits unstable. Energy could dissipate so rapidly that stars flicker out in millennia, or so slowly that heat death takes trillions of years longer than in our cosmos. Matter might assemble into hyperstructures we can't even visualize, shapes with more symmetry than a crystal, more complexity than a fractal. The kicker: we may never detect these alternate realities directly. The space between bubble universes could be expanding faster than light, putting them forever beyond our horizon. Quantum branches might exist in Hilbert space, a mathematical abstraction rather than a physical location. Yet the multiverse isn't just a flight of fancy, it's a framework that solves real puzzles, like why our universe's constants are so finely tuned for life. If every possible configuration exists somewhere, it's no surprise we find ourselves in one where matter and energy conspired to make us possible. So the next time you gaze at the night sky, consider this. You might be looking at just one page in an infinite cosmic library, where every shelf holds a universe with its own rules, its own history, its own version of the dance between matter and energy. And somewhere in that vast collection, there could be a reality where the stars tell a completely different story. You might think a vacuum is the emptiest thing imaginable, a void where nothing exists, not even air. But the universe has a surprise for us. What we call empty space is actually a seething, bubbling ocean of energy, alive with activity on scales so tiny we're only beginning to grasp them. This is vacuum energy, the hidden heartbeat of reality itself, where particles flicker in and out of existence so fast they defy the very laws of classical physics. Imagine a cosmic game of whack-a-mole, where electrons and positrons pop up spontaneously, borrow energy from nowhere, and vanish again before we can measure them directly. These aren't just mathematical quirks, they're proof that even in the deepest void, the universe refuses to sit still. The implications are staggering. Take the Casimir effect, where 2 uncharged metal plates placed microscopically close in a vacuum inexplicably pull toward each other. Why? Because the space outside the plates allows for more quantum fluctuations than the narrow gap between them, creating a pressure differential that nudges them together. It's like being in a crowded room where the noise is louder on one side, gently pushing you toward the quieter space. This isn't theoretical, it's been measured in labs, confirming that so-called nothingness exerts real, measurable forces on matter. But vacuum energy's influence doesn't stop at the quantum scale. Some cosmologists believe it's the engine behind dark energy, the mysterious force accelerating the expansion of the universe. Here's the puzzle. If empty space contains this intrinsic energy, then as the universe grows, more space appears, and with it more vacuum energy. This could explain why galaxies are flying apart faster and faster, as if space-time itself is being stretched from within. Yet there's a catch. When we calculate how much energy the quantum vacuum should have, the numbers are off by a factor of 10 to the power of 120. That's like predicting a teacup of water but discovering an ocean larger than the observable universe. Clearly, we're missing something fundamental, the wildest part. Vacuum energy might hold the key to understanding the universe's ultimate fate. If it's truly constant, the cosmos could expand forever, cooling into a dark, lifeless void. But if it decays, if the vacuum's energy suddenly drops, it could trigger a catastrophic phase transition, rewriting the laws of physics in an instant. Picture a bubble of true vacuum forming somewhere in space, expanding at light speed and erasing everything in its path, from atoms to galaxies. It sounds apocalyptic, but the math suggests it's possible. The good news: if such an event hasn't happened in 13.8 billion years, it's unlikely to start now. So the next time you look at the night sky, remember, the vast darkness between stars isn't passive or inert. It's a dynamic, crackling field of potential, where particles dance in and out of reality, and the fate of the cosmos is quietly being written. What we call empty space is anything but. It's the universe's most underrated performer, playing a role in everything from subatomic forces to the destiny of galaxies. And we're only just beginning to hear its story. Imagine flipping a light switch and the bulb glows forever without needing more power, or trains that glide frictionless above their tracks at impossible speeds. This isn't science fiction, it's the promise of superconductivity, one of nature's most baffling behaviors, where certain materials, when chilled to extreme temperatures, suddenly let electricity flow without any resistance at all. No heat, no loss, just pure, unimpeded current. The implications are staggering: power grids that waste zero energy, MRI machines with unprecedented precision, even quantum computers operating flawlessly at scales we've only dreamed of. But how does this defiance of physics actually work? At its heart, superconductivity is a quantum party where electrons stop behaving like individual particles and start acting as a synchronized collective. Normally, electrons bump and jostle through metals, losing energy as heat. That's resistance. But in a superconductor cooled below its critical temperature, something extraordinary happens. Electrons pair up through interactions with the material's atomic lattice, forming what physicists call Cooper pairs. These pairs don't scatter like solo electrons, they move in lockstep, as if dancing on a frictionless floor. It's like rush hour traffic suddenly transforming into a perfectly coordinated parade where every car moves in harmony, never touching, never slowing. The discovery of this phenomenon reads like a scientific fairy tale. In 1911, Dutch physicist Kármán was experimenting with mercury near absolute zero when he noticed its electrical resistance didn't just decrease, it vanished entirely. Later, in 1957, the BCS theory, named for Bardeen, Cooper, and Schrieffer, finally explained the microscopic mechanism behind this magic. But the story didn't end there. In the 1980s, researchers stumbled upon high-temperature superconductors, ceramic materials that lost resistance at comparatively balmy temperatures, still cryogenic, but far warmer than expected. These materials defied BCS theory, hinting that we'd only scratched the surface of how matter can cheat resistance. Today, the race is on to crack room temperature superconductivity, a discovery that would rewrite energy technology overnight. Picture power lines spanning continents without losing a watt, or ultra-efficient wind turbines generating electricity with near-perfect conversion. Medical imaging would leap forward, with MRI machines ditching bulky cooling systems for compact, high-resolution scanners. Even transportation would transform maglev trains, currently limited to specialized tracks, could become as common as subways, silently floating on magnetic fields generated by superconducting coils. Yet the deepest mystery remains. What if superconductivity isn't just a quirky material property, but a window into how matter and energy interact under extreme conditions? Some theories suggest that similar electron pairing might occur in neutron stars, where unimaginable pressures create exotic states of matter. Others speculate that understanding superconductivity could help unravel high-energy physics puzzles, from dark matter to the early universe's symmetry breaking. Every time we push the boundaries of this phenomenon, we're not just engineering better materials, we're probing the universe's hidden rulebook, one chilled electron at a time. So while superconductors might seem like a niche lab curiosity today, they could hold the key to tomorrow's energy revolution. And somewhere in that quantum dance of electrons, the universe might be whispering clues to a future where energy flows as effortlessly as light through space. The universe is teeming with possibilities, billions of galaxies, each with billions of stars, many orbited by planets in the so-called Goldilocks zone, where conditions are just right for life. Given the staggering numbers, the cosmos should be buzzing with civilizations, their signals crisscrossing the void like a cosmic internet. Yet when we listen, all we hear is silence. This is the Fermi paradox in a nutshell. If matter and energy have conspired to create us, why haven't they produced others we can detect? Where is everybody? One answer might lie in the sheer scale of time. Civilizations could rise and fall in cosmic blinks, leaving only faint traces. Imagine an ant colony sprouting on Monday and vanishing by Friday. Would anyone notice? Earth has been habitable for billions of years, but human civilization has only existed for a few thousand, and radio technology for barely over a century. If advanced societies are rare or short-lived, we might simply be out of sync with the universe's other storytellers, our broadcasts lost in the vastness before they reach anyone. Then there's the Great Filter Hypothesis, a cosmic bottleneck that prevents life from reaching interstellar stages. Maybe the leap from simple chemistry to complex life is astronomically unlikely, or perhaps intelligent species inevitably destroy themselves with technology. The eerie silence could mean we've already passed the filter, making us a cosmic fluke, or worse, that the real test lies ahead, and civilizations like ours rarely survive it. But not all explanations are so grim. Advanced civilizations might transcend physical forms, uploading their consciousness into digital realms or harnessing dark energy in ways we can't yet fathom. Their signals could be all around us, encoded in neutrino bursts or gravitational waves, waiting for us to develop the right tools to decode them. Or consider the possibility that we're like islanders unaware of the ocean. What if galactic civilizations thrive in clusters, and we're just in the cosmic boonies, too remote to notice? The truth is, the Fermi paradox isn't just about aliens, it's a mirror. Every possible answer forces us to confront humanity's place in the universe. Are we the first, the last, or simply one voice in a chorus we're not yet advanced enough to hear? Until we know, the silence isn't empty, it's a question, echoing across the stars. Exoplanets aren't just dots of light in a telescope, they're entire worlds, each with its own story of how matter and energy conspired to create landscapes stranger than anything in our solar system. Take WASP 76b, a gas giant so close to its star that daytime temperatures soar above 4,000 degrees Fahrenheit, hot enough to vaporize iron. On its night side, this molten metal rains down in a perpetual storm, a cycle of destruction and rebirth playing out across scorching skies. Then there's Gliese 436b, a planet with an ocean, not of water, but of superfluid helium, a bizarre state of matter that flows without friction, defying gravity's pull like something from a dream. These aren't just curiosities, they're proof that the universe has a far richer imagination than we do. The hunt for these alien worlds began in earnest in 1995, when astronomers spotted 51 Pegasi b, a Jupiter-sized planet orbiting its star in just 4 days. Since then, we've found over 5,000 exoplanets, from diamond-rich worlds like 55 Cancri E to rogue planets drifting untethered through interstellar space. What's revolutionary isn't just their existence, it's how they've shattered our assumptions. We once thought solar systems like ours were the norm, with small, rocky planets close to their stars and gas giants farther out. Then along came hot Jupiters, massive planets hugging their stars closer than Mercury orbits the Sun, and super-Earths, rocky worlds up to 10 times heftier than our own, rewriting the rulebook on planetary formation. But the real prize lies in the Goldilocks zone, the region around a star where temperatures are just right for liquid water. Kepler 442b, 1,200 light-years away, was one of the first Earth-sized candidates found in this habitable sweet spot. Then came TRAPPIST-1, a dwarf star with 7 rocky planets, 3 of which might have the right conditions for oceans. The catch: these worlds are tidally locked, with one side permanently baked in sunlight and the other shrouded in eternal night. Could life thrive in the twilight between? Or take Proxima Centauri b, our closest exoplanetary neighbor at just 4 light-years away. Bathed in intense radiation from its red dwarf star, its surface might be sterilized by flares unless it has a thick atmosphere or underground oceans to shelter fragile chemistry. What makes these discoveries so profound isn't just the diversity, it's what they reveal about matter's potential. On Earth, carbon-based life thrives in water, but on Titan, Saturn's moon, methane rivers might host entirely different biochemistries. Could exoplanets push this further? Imagine silicon-based life forms in scorching deserts, or organisms swimming in ammonia seas on frozen worlds. The building blocks are universal hydrogen, oxygen, carbon, but the recipes are limitless. Yet the greatest revelation might be existential. Every exoplanet found in a habitable zone whispers the same question. If the universe has crafted so many worlds where matter and energy align just right, how many times has it sparked life? We're no longer guessing, we're counting. And with telescopes like James Webb analyzing atmospheres for oxygen, methane, or even industrial pollutants, we're not just searching for planets anymore. We're hunting for neighbors, so when you look up tonight, remember, those faint stars aren't just lights. They're suns circled by worlds where mountains might glow under twin sunsets, where oceans could ripple under alien moons, and where perhaps someone else is gazing back at our pale blue dot, wondering the same thing. What if the universe isn't built from particles at all, but from tiny, vibrating loops of energy, each humming its own unique note in a cosmic symphony? This is the radical vision of string theory, where electrons, quarks, and even the fabric of spacetime itself aren't fundamental dots but shimmering strands, so small that if an atom were the size of our solar system, a string would barely span a football field. These aren't just abstract threads, they're the universe's most basic instruments, vibrating at different frequencies to create the particles we perceive as matter and energy. Pluck one way and you get an electron, pluck another and it becomes a photon. In this framework, the entire cosmos might be an intricate composition played out across 11 dimensions, with gravity, light, and matter all emerging from the same underlying melody. The beauty of string theory lies in its ambition to unify physics' greatest puzzles. For decades, quantum mechanics and general relativity have been at odds, one ruling the subatomic world with probability and uncertainty, the other governing stars and galaxies with smooth spacetime curves. Strings could bridge this divide. Imagine a violin string. Its vibrations create distinct notes, just as a string's oscillations manifest as different particles. Even gravity, which stubbornly resists quantum description, might arise naturally from closed loops of strings vibrating through higher dimensions. It's as if Einstein's cosmic stage and the quantum orchestra finally share the same sheet music. Yet the theory's elegance comes with dizzying implications. To work mathematically, strings require extra dimensions, not just the 3 of space and 1 of time we experience, but 6 or 7 more, curled into shapes so tiny we'd never notice them. Picture a garden hose. From afar, it looks one-dimensional, but up close, it reveals a circular dimension wrapping around its length. Strings might dance through similar hidden geometries, called Calabi-Yau manifolds, their vibrations shaped by these unseen folds in reality. Some versions of the theory even suggest parallel universes floating like bubbles in a higher dimensional foam, each with its own unique set of physical laws. But string theory isn't just about esoteric math, it's reshaped how we think about black holes. In the 1990s, physicists discovered that strings could explain the entropy of these cosmic enigmas, matching predictions made decades earlier by Stephen Hawking. A black hole's event horizon, in this view, might be a tangled web of strings, their vibrations encoding the information of everything that falls inside. This holographic principle suggests that our 3-dimensional reality could be a projection of information stored on a 2-dimensional surface, like a cosmic vinyl record playing the universe into existence. The catch: strings are so small that direct evidence remains elusive. The energy needed to probe their scale is a quadrillion times beyond what our best particle colliders can achieve. Yet indirect clues might lie in cosmic echoes from the Big Bang or subtle gravitational anomalies. And if strings are real, they'd imply a universe far richer than we've imagined, one where matter, energy, and even the laws of physics are just harmonies in a deeper, vibrational reality. So the next time you hear a melody, consider this. The universe might be singing its own song, with every atom, every beam of light, and every ripple in spacetime born from the same cosmic strings humming in the dark. Whether we'll ever hear that music clearly remains an open question, but the search itself is rewriting the score of modern physics. The holographic principle turns everything we think we know about reality inside out, literally. Imagine your entire life, from the phone in your hand to the stars overhead, isn't truly 3-dimensional but a spectacular illusion, like a movie projected from data encoded on a distant, flat surface. This isn't science fiction. It's a serious theory born from the study of black holes, where the information swallowed by their immense gravity isn't lost but smeared across their 2-dimensional event horizons like cosmic graffiti. If that's true for black holes, could the entire universe work the same way? Think of it like a credit card hologram, those shimmering images that seem to hover above the plastic. The depth and movement are convincing, but they're just clever tricks of light interacting with microscopic grooves etched into the card's surface. Now scale that up to cosmic proportions. What if the galaxies, planets, and even your own body are just incredibly detailed projections from a hidden, lower-dimensional layer of reality? The mathematics behind this idea isn't just speculative, it resolves real paradoxes, like how black holes can simultaneously destroy information yet obey quantum mechanics' strict no-deletion rule. Here's where it gets even wilder. If the holographic principle holds, matter and energy as we experience them might be secondary actors in the universe's grand play. The real drama could be happening on an unimaginably thin boundary at the edge of existence, where bits of information interact like pixels on a screen, rendering the rich, textured world we perceive. This would mean that every particle collision, every supernova explosion, even the firing of neurons in your brain, is just the visible output of deeper, simpler processes unfolding in a realm we can't see. The implications ripple across physics. Take gravity, the force that sculpts galaxies and pins us to Earth. In a holographic universe, gravity might not be a fundamental force at all but an emergent property, like how the wetness of water emerges from countless molecules, even though no single molecule is wet. This could explain why gravity is so weak compared to other forces. It's not a primary feature of reality, just a side effect of the projection. Even time might lose its status as a fundamental dimension, becoming more like a narrative device the universe uses to organize information. But how could we test such a mind-bending idea? Surprisingly, there are clues. Some physicists search for pixelation in spacetime at the tiniest scales, like graininess in a photograph enlarged too far. Others analyze cosmic microwave background radiation for anomalies that might hint at a two-dimensional origin. The most tantalizing evidence comes from quantum entanglement, where particles instantly influence each other across vast distances, a phenomenon that makes perfect sense if they're actually linked at a deeper, non-local level, like 2 points on the same holographic film. What's at stake isn't just a new model of the cosmos, but a complete redefinition of existence. If the holographic principle is true, then matter and energy aren't the building blocks of reality. They're the end products of a vast, hidden computation. The dance we've been observing between them might be nothing more than shadows on the wall of a far stranger, simpler realm. And somewhere in that realization lies a humbling truth. The universe isn't just more mysterious than we imagine. It's more mysterious than we can imagine. Neutrinos are the universe's ultimate ghosts, particles so elusive they can pass through entire planets like moonlight through glass. Born in the hearts of stars, the fury of supernova, and even the decay of atoms in your own body, these nearly massless phantoms carry whispers of cosmic events too distant or violent for light alone to reveal. Every second, trillions of them stream through you unnoticed, leaving no trace, their presence betrayed only by the most ingenious experiments humanity has ever devised. Take the sun, for example. While sunlight takes 8 minutes to reach Earth, the neutrinos produced in its core arrive almost instantly, having slipped through the star's dense layers without a single collision. These solar neutrinos are like telegrams from the sun's nuclear furnace, carrying unfiltered news of the fusion reactions powering our solar system. Yet when scientists first tried to count them in the 1960s, they found only a third of the expected number, a discrepancy that baffled researchers for decades. The solution: neutrinos aren't just one type of particle. They shape-shift between 3 flavors: electron, muon, and tau as they travel. A quantum quirk called neutrino oscillation that proved these phantoms have mass, however infinitesimal. Detecting them requires equal parts patience and ingenuity. Consider the Super Kamiok and Observatory in Japan, a colossal tank buried deep underground, filled with 50,000 tons of ultra-pure water and lined with sensors. When a rare neutrino does interact with a water molecule, it emits a faint blue flash Cherenkov radiation like a cosmic fingerprint. Even then, most neutrinos pass right through the detector, leaving scientists to sift through mountains of data for a handful of meaningful collisions. It's like listening for a whisper in a hurricane, but the payoff is extraordinary. In 1987, neutrinos from a supernova in the Large Magellanic Cloud reached Earth hours before the star's visible light, offering astronomers their first real-time alert of a stellar explosion. More recently, neutrino observatories traced high-energy particles back to blazars supermassive black holes shooting jets of radiation across the cosmos, proving these ghosts can map the universe's most energetic phenomena. Some theories even suggest neutrinos might hold clues to dark matter or the imbalance between matter and antimatter that made our existence possible. What makes these particles so fascinating isn't just their stealth, it's their refusal to play by ordinary rules. They ignore magnetism, shrug off gravity, and barely interact with matter at all. Yet in their silence, they carry stories of cosmic cataclysms, the inner workings of stars, and possibly even the birth of the universe itself. So the next time you feel a sudden, inexplicable chill, remember, it might just be a neutrino, fresh from a stellar explosion halfway across the galaxy, passing through you like a shadow through a dream. Somewhere beyond the stars, hidden behind the veil of the Milky Way's dust and stars, lies a gravitational anomaly so powerful it's dragging entire galaxies toward it at mind-bending speeds. Astronomers call it the Great Attractor, a cosmic heavyweight exerting its pull across hundreds of millions of light years, yet remaining utterly invisible to our telescopes. This isn't just a concentration of known matter. The sheer scale of its influence suggests something far more profound, a gravitational fingerprint without a visible hand. Picture the universe as a vast, flowing river. Galaxies aren't just drifting randomly, they're caught in currents shaped by the distribution of matter and energy. In the 1970s, scientists mapping these cosmic flows noticed something peculiar. Our local galactic neighborhood, including the Milky Way, is being pulled toward a specific point in space near the constellation Centaurus, moving at over 2 million kilometers per hour. The odd part, when they looked in that direction, they found only a sparse collection of galaxies nowhere near enough to account for the tremendous gravitational tug. It would be like feeling hurricane-force winds in your backyard, but when you step outside, there's not even a breeze. One leading theory points to dark matter, the universe's invisible scaffolding clustered in unimaginable densities. If dark matter makes up 85% of the universe's mass, as current models suggest, then the Great Attractor could be a massive knot in this shadowy web, its gravity warping spacetime without emitting any light. Supporting this idea is the Shapley supercluster, a staggering collection of galaxies about 650 million light-years beyond the Attractor, which might be amplifying its pull like a cosmic magnifying glass. But there's a twist. Some researchers propose the Attractor isn't the final destination at all. It's just one stop on a far grander journey. Observations suggest our galaxy, along with thousands of others, might ultimately be flowing toward an even more massive structure dubbed the dipole repeller, a vast region of space so empty that its lack of gravitational pull effectively pushes galaxies away. This would mean the Great Attractor isn't just pulling us, it's caught in a tug of war with cosmic voids, a dynamic interplay between presence and absence sculpting large-scale motion. The challenge in solving this mystery lies in our own celestial backyard. The Milky Way's dense disk of stars and dust blocks our view of the Attractor's central region, leaving us to piece together clues from indirect measurements. New tools like infrared and radio telescopes are peeling back this obscuring layer, revealing galaxy clusters previously hidden behind the cosmic curtain. Each discovery adds another piece to the puzzle, whether it's strange radio emissions hinting at unseen structures or peculiar galaxy alignments suggesting deeper gravitational currents. What makes the Great Attractor so compelling isn't just its hidden nature, It's what it reveals about our place in the cosmos. We're not stationary observers on a quiet planet. We're passengers on a galactic voyage, swept along by forces we're only beginning to map. And somewhere in that darkness, the universe is hiding one of its most powerful engines, reminding us that what we see is only a fraction of what's truly out there. If black holes are the universe's ultimate vacuum cleaners, sucking in everything that crosses their path, then white holes would be their cosmic fire hoses, blasting matter and energy outward with unstoppable force. These hypothetical objects, first proposed as mathematical solutions in Einstein's equations of general relativity, flip the script on everything we know about singularities. Where a black hole's event horizon is a point of no return, a white hole's boundary would be a point of no entry. Nothing could cross inside, not even light. Instead of pulling spacetime inward like a drain, it would push outward like an erupting geyser, violently expelling whatever was trapped within. Imagine stumbling upon a white hole in deep space. Unlike the eerie darkness surrounding a black hole, this object would glow with unimaginable brilliance, its surface radiating energy at temperatures that dwarf the cores of stars. Any matter fortunate enough to escape would be hurled across the cosmos at relativistic speeds, like debris from a celestial cannon. Theoretically, a white hole could be the other end of a black hole's tunnel, a wormhole exit where everything swallowed by the singularity is violently reborn somewhere else in the universe. It's a tantalizing idea, suggesting black holes might not be eternal prisons after all, but cosmic recyclers turning destruction into creation. The catch: no one has ever observed a white hole, and many physicists argue they can't exist in our universe, at least not for long. The second law of thermodynamics suggests such an object would be inherently unstable, like a building perpetually exploding but never collapsing. Any realistic white hole would likely transform into a black hole almost instantly, its outpouring energy collapsing back under its own gravity. Yet some theories speculate that the Big Bang itself might have been a white hole event, a singular eruption of space-time and energy from an unknowable source. Others propose that tiny, short-lived white holes could explain mysterious gamma-ray bursts or even dark matter's origins. Even if they remain purely theoretical, white holes challenge our understanding of cause and effect. They hint at a universe where time's arrow might not always point forward, where singularities could bridge distant regions of space-time, and where destruction in one corner of the cosmos might seed creation in another. Whether they're mathematical curiosities or hidden actors in the cosmic drama, white holes remind us that the universe's rulebook still has pages we haven't read, and some that might rewrite themselves entirely. Zoom in far enough, past atoms beyond quarks deeper than any microscope can see, and the smooth fabric of space-time we take for granted begins to churn like a stormy sea. This is quantum foam, the universe's most chaotic basement level, where the rules of gravity and quantum mechanics collide in a frenzy of virtual particles, wormholes, and space-time bubbles flickering in and out of existence. At scales of a Planck length, that's a millionth of a billionth of a billionth of a billionth of a centimeter, the very stage upon which matter and energy perform their dance dissolves into a turbulent foam, making empty space anything but empty. Picture trying to measure the surface of a lake during a hurricane. Your ruler would shake violently, your measurements fluctuating wildly with each wave. Now imagine that instability is baked into reality itself, not as a flaw but as a fundamental feature. In quantum foam, space-time isn't smooth and continuous. It's a seething froth where tiny wormholes and black holes blink into existence, borrowing energy from the vacuum before vanishing again. These aren't just mathematical oddities, they're the universe's way of balancing the books at microscopic scales, where Heisenberg's uncertainty principle allows energy to appear out of nowhere so long as it disappears fast enough. This chaos has real consequences. Light traveling across the cosmos doesn't glide through perfectly empty space, it stumbles through this froth, like a hiker navigating a rocky trail. Over vast distances, these quantum bumps could subtly alter a photon's path or energy, an effect astronomers have hunted for in the light of distant gamma-ray bursts. Even more intriguing, some theories suggest quantum foam might explain why gravity refuses to play nice with quantum mechanics. At these scales, spacetime's frothiness could smear out singularities, preventing the infinite densities that break physics equations. Yet the wildest implication might be how quantum foam blurs the line between existence and illusion. If spacetime is inherently foamy, then the solid, predictable universe we experience is just an average, a cosmic smoothing out of unimaginably tiny fluctuations. It's like watching a movie projected from a damaged film reel. The individual frames are jagged and chaotic, but played at speed, they create the illusion of seamless motion. Our reality, in this view, might be the universe's ultimate sleight of hand, a magician's trick performed at Planck-scale speeds. The real challenge, we can't directly observe this foam. Its effects are too tiny, its timescales too brief, but ingenious experiments are inching closer. Some physicists analyze the spin of distant pulsars for signs of spacetime's granularity disrupting their signals. Others use ultra-precise atomic clocks to detect minute time fluctuations that could betray the foam's turbulence. Each failed detection narrows the possibilities, inching us toward understanding whether quantum foam is the universe's hidden foundation, or just a fascinating dead end in our quest to unify physics. One thing's certain, if quantum foam is real, it means the universe's calm, orderly facade is just that, a facade. Beneath the surface, reality is a boiling, bubbling frenzy where matter, energy, and spacetime itself are locked in a dance so chaotic, it makes black holes look tame. And somewhere in that froth, the answers to physics' biggest riddles might be hiding if we can only learn to read the foam's ephemeral patterns. Earth doesn't just orbit the sun, it occupies a cosmic sweet spot where matter and energy perform an exquisitely balanced duet. This Goldilocks zone, where temperatures allow liquid water to persist, isn't just about distance from a star. It's a fragile interplay of atmospheric composition, planetary mass, and stellar temperament that transforms chemistry into biology. Consider Venus and Mars, both technically within our solar system's habitable zone. One became a pressure cooker with runaway greenhouse gases, the other a frozen desert with a whisper-thin atmosphere. Earth's stability emerges from countless factors: a magnetic field deflecting deadly solar winds, plate tectonics recycling carbon to regulate temperatures, even Jupiter's gravity sweeping away asteroids that might have sterilized our planet repeatedly. The search for other life-friendly zones reveals just how extraordinary this equilibrium is. Take Kepler 452b, a super-Earth orbiting a star 5 billion years older than our Sun. At first glance, its position seems perfect until you realize its aging sun has likely baked away any oceans, leaving a scorched wasteland. Or Proxima Centauri b, tantalizingly close at 4 light-years, but so irradiated by its red dwarf star's flares that any atmosphere may have been stripped away eons ago. These worlds highlight the Goldilocks zone's true complexity. It's not a static belt, but a shifting interplay of stellar evolution, planetary geology, and cosmic luck. Yet the universe continually surprises us. Deep beneath the icy crust of Europa, Jupiter's moon, gravitational kneading from the gas giant may maintain a subsurface ocean twice Earth's volume, proof that habitable conditions can exist far outside traditional zones. Around dim red dwarfs, tidally locked planets might harbor life in narrow twilight bands where temperatures allow liquid water. Even rogue planets ejected from their star systems could sustain subterranean warmth from radioactive decay for billions of years. The definition of habitable is expanding as we discover how creatively matter and energy can conspire to nurture complexity. What makes Earth's position truly remarkable isn't just its present stability, it's the longevity of its favorable conditions. While many exoplanets may briefly pass through habitable phases, Earth has maintained temperate conditions for nearly 4 billion years, allowing life to evolve through countless cosmic upheavals. This endurance suggests that the rarest ingredient for life might not be liquid water or organic molecules, but time, enough uninterrupted epochs for matter to self-organize into ever more intricate forms. As we scan the stars for other pale blue dots, we're not just hunting for planets that could host life today, but worlds where the dance between matter and energy has been gentle, persistent, and patient enough to let the universe become aware of itself. Time crystals aren't just another exotic state of matter, they're a cosmic paradox made real. Imagine a snowflake that doesn't just repeat its pattern in space but in time, pulsing between configurations without any energy input, forever out of sync with the universe's relentless march toward equilibrium. This isn't science fiction. In 2016, Nobel laureate Frank Wilczek's theoretical prediction became reality when researchers created the first time crystals using chains of ytterbium atoms, chilled to near absolute zero and nudged with precise laser pulses. Unlike all other matter which settles into equilibrium, these structures pulse rhythmically like atomic metronomes, their atoms flipping spins in perfect, persistent cycles without slowing or dissipating energy. What makes time crystals so revolutionary is how they sidestep one of physics' most sacred laws, the second law of thermodynamics. Normally, any system left alone will eventually run down. Ice melts, pendulums stop, even stars exhaust their fuel. But time crystals exist in a perpetual, out-of-equilibrium state, not despite the laws of physics but because of a clever loophole. By carefully arranging quantum interactions, scientists engineered a scenario where the system's lowest energy state isn't stillness but eternal oscillation. It's like winding a clock once and having it tick forever without springs or weights, powered by the quantum equivalent of a perfectly timed nudge. The implications ripple across multiple frontiers. For quantum computing, time crystals could provide ultra-stable qubits resistant to decoherence, the bane of quantum systems that causes them to lose information. In precision sensors, their rhythmic pulses might measure time or magnetic fields with unprecedented accuracy. Some theorists even speculate they could model complex systems like black holes, where matter behaves in similarly bizarre, time-defying ways. Yet the most tantalizing possibility lies in fundamental physics. Time crystals force us to rethink what phase of matter even means. We're used to solids, liquids, and gases being defined by spatial order. But what if time, not just space, can crystallize? Creating these structures pushes experimental limits. Most time crystals so far exist for milliseconds in lab conditions colder than interstellar space. But recent breakthroughs show they can form at room temperature in diamond defects, hinting at practical applications. The challenge now is scaling them. Imagine a material that self-regulates its atomic vibrations to never wear out, or a quantum memory that preserves information indefinitely. Perhaps time crystals' greatest gift is perspective. They prove that matter and energy can dance to rhythms we're only beginning to hear, in a universe far stranger than equilibrium-bound physics suggested. Every pulse whispers a question. What other impossible seeming states might be waiting in the quantum code, ready to rewrite our understanding of reality's building blocks? The Kármán line isn't just an arbitrary border. It's where Earth's embrace finally loosens and the cosmos takes over. At 100 kilometers above sea level, the air becomes so thin that traditional aircraft can no longer rely on wings for lift. Yet this isn't a sudden wall between atmosphere and space. It's a shimmering threshold where matter and energy trade dominance in a delicate ballet. Here, the few remaining air molecules are so sparse that they travel kilometers before colliding, while solar radiation bombards them with unchecked fury, ionizing atoms into a faint, glowing plasma. This is the realm where spacecraft must fight to stay aloft, yet satellites can glide for years, a paradox of physics playing out at the edge of two worlds. What makes this boundary so fascinating is how it defies simple definition. The Kármán line isn't where the atmosphere disappears, it's where it changes character. Below it, weather systems churn and life thrives on chemical energy. Above it, atomic oxygen dominates, ultraviolet light fractures molecules, and the vacuum of space begins its steady claim. Satellites in low Earth orbit still grapple with traces of atmosphere, their orbits slowly decaying from the drag of these wisps of gas. Meanwhile, the auroras dance just below this line, where charged particles from the solar wind slam into Earth's magnetic field, transforming kinetic energy into shimmering light. It's as if the universe itself can't decide where Earth ends and space begins. This liminal zone is also a laboratory for extreme science. Hypersonic vehicles skirting the Kármán line face temperatures hot enough to melt steel, as air friction converts motion into blistering heat. Yet a few kilometers higher, the cold of space drops to hundreds of degrees below freezing, with no medium to transfer warmth. Engineers designing spacecraft must account for this razor-thin margin where materials face both infernos and ice within minutes of ascent. Even the behavior of flames changes here without buoyancy. Fire doesn't rise but forms eerie, spherical balls of combustion, revealing how deeply gravity and atmospheric pressure shape energy's dance. Perhaps most compelling is how this boundary reflects Earth's story. The gases thinning at the Kármán line are the same ones that, denser below, shield life from cosmic rays and meteors. The transition isn't just spatial but temporal, a snapshot of our planet's gradual loss of atmosphere over billions of years, molecule by molecule, to the solar wind. Future astronauts crossing this line won't just be leaving Earth. They'll be tracing the path of every atom that ever escaped our world's grip, joining the grand interstellar cycle where matter and energy endlessly reconfigure. So while the Kármán line might appear on charts as a neat, round number, it's really a testament to nature's refusal to be boxed in. It's where Earth's breath fades into the cosmic wind, where the rules of aerodynamics yield to orbital mechanics, and where humanity's home ends not with a wall but with a whisper. The sun isn't just a distant ball of light. It's an active, sometimes violent neighbor, hurling storms of charged particles our way with enough force to knock out satellites, disrupt radio communications, and even plunge entire regions into darkness. These eruptions, known as solar flares and coronal mass ejections, unleash energy equivalent to billions of hydrogen bombs, twisting Earth's magnetic field like taffy and sparking dazzling auroras, while threatening the delicate electronic infrastructure modern life depends on. In March 1989, a geomagnetic storm triggered by a solar flare blacked out Quebec's power grid in seconds, leaving 6 million people without electricity for 9 hours. But that was just a warning shot. The Carrington event of 1859, the most powerful solar storm ever recorded, set telegraph stations ablaze and painted the skies so brightly that miners in the Rocky Mountains woke up thinking it was dawn at midnight. If a storm like that hit today, experts estimate it could cause up to $2 trillion in damages globally, knocking out GPS systems, crippling financial networks, and leaving some areas without power for months. What makes these solar tantrums so dangerous isn't just their raw power, it's how they exploit Earth's invisible vulnerabilities. When a coronal mass ejection reaches our planet, its charged particles collide with the magnetosphere, the magnetic bubble shielding us from the solar wind. Normally, this field deflects most threats, funneling particles harmlessly toward the poles where they create the northern and southern lights. But during extreme storms, the magnetosphere can become overloaded, inducing powerful electric currents in long conductors like power lines and pipelines. These geomagnetically induced currents, essentially rogue electricity with nowhere to go, can fry transformers, melt circuitry, and cascade through grids like a domino effect. The irony, the same technology that makes us vulnerable also offers solutions. Spacecraft like NASA's Solar Dynamics Observatory and the European Space Agency's Solar Orbiter now monitor the Sun 24/7, providing crucial warnings when eruptions head our way. Power companies are hardening grids with transformers designed to withstand surges, while satellite operators can put sensitive electronics into safe mode during storms. Even astronauts on the International Space Station have protocols, retreating to shielded compartments when radiation levels spike. Yet the biggest challenge isn't technical, it's temporal. Solar activity follows an 11-year cycle, with periods of calm solar minimum and chaos solar maximum. We're currently approaching the peak of solar cycle 25, expected to hit its zenith in 2025. But predicting specific storms remains frustratingly imprecise, like forecasting hurricanes without knowing which way the wind will blow. That's why scientists are racing to improve models, using AI to analyze centuries of solar data, and even studying ancient tree rings for traces of prehistoric megaflares. The stakes couldn't be higher. In a world where everything from banking to agriculture relies on precision timing from GPS satellites, and where interconnected power grids span continents, a single well-aimed solar punch could send shockwaves through civilization itself. But there's hope. By treating space weather like the existential threat it is and investing in early warning systems, resilient infrastructure, and international cooperation, we can transform our relationship with the sun from one of vulnerability to one of vigilance. After all, the same star that gives us light and warmth also reminds us, in its occasional fury, that we're not just inhabitants of Earth, but citizens of a solar system far more dynamic than we often realize. The Drake equation isn't just a formula, it's a mirror held up to the cosmos, forcing us to confront how matter, energy, and sheer chance might weave together to create civilizations among the stars. Conceived by astronomer Frank Drake in 1961, this deceptively simple string of variables transforms existential wonder into quantifiable probabilities. At its core, the equation multiplies factors like the rate of star formation, the fraction of stars with planets, and the odds of life emerging on those planets, ultimately estimating how many intelligent species could be sharing the Milky Way with us right now. But beneath these numbers lies a profound truth. Every term in the equation is a battleground where physics, chemistry, and biology collide. Take the first variable, stellar birth rates. Our galaxy produces about 7 new stars per year, each a potential crucible for planetary systems. But not all stars are equal. Massive blue giants burn out in millions of years, leaving little time for life to evolve, while diminutive red dwarfs may bathe their planets in deadly flares. The sweet spot, sun-like stars, stable for billions of years, offering the extended runway complex chemistry needs. Yet even with ideal stars, planets must orbit within the habitable zone where matter organizes into liquid water, not too close to boil it all away, not too far to freeze it solid. Kepler telescope data suggests 1 in 5 Sun-like stars host an Earth-sized world in this zone. That's billions of potential incubators in our galaxy alone. But matter must perform miracles to leap from chemistry to biology. The next term's fraction of planets where life appears and where intelligence evolves are where equations blur into philosophy. On Earth, life emerged almost as soon as conditions allowed, hinting that given the right energy and ingredients, biology might be inevitable. Yet the transition from single-celled organisms to tool-building civilizations took 3 billion years, suggesting intelligence is far from guaranteed. Some worlds might remain forever microbial, their oceans teeming with algae but never poets. Others could develop technological species only to succumb to asteroid impacts or their own inventions, their radio signals fading before we ever tune in. This is where energy enters the equation not just as starlight, but as a societal currency. Civilizations advanced enough to communicate across space likely harness enormous power, whether through Dyson spheres capturing a star's full output or fusion reactors mimicking stellar cores. Such signatures, unnatural infrared glows or neutrino patterns, could betray their presence long before radio signals arrive. Yet the final variable, the average lifespan of communicative civilizations, looms largest. If most societies self-destruct within centuries of discovering radio, the galaxy might be littered with silent ruins. But if even a fraction endure for millennia, the cosmic airwaves could be buzzing with conversation. The Drake equation's power lies not in its answers, but in how it reframes our place in the universe. Plug in optimistic numbers, and the Milky Way might host thousands of civilizations at this moment. Pessimistic estimates suggest we could be alone, a single flicker of awareness in an ocean of dead matter. But perhaps the most humbling possibility lies between these extremes. That intelligence is rare enough to make each instance precious, yet common enough to transform the cosmos from a void into a network of minds. Every time we point a telescope at an exoplanet or scan the sky for artificial signals, we're not just searching for aliens, we're testing whether matter and energy, given enough time and the right conditions, inevitably turn toward consciousness. And that makes every star we see not just a light in the dark, but a question waiting to be answered. The dance between matter and energy isn't just the universe's foundation. It's its greatest performance, an endless symphony where every particle, every beam of light, every swirling galaxy is both performer and audience. From the moment energy crystallized into the first atoms after the Big Bang, to the way black holes warp spacetime into gravitational pirouettes, this cosmic ballet has shaped everything we are and everything we see. And yet, for all we've uncovered entangled particles whispering across light years, vacuum energy bubbling beneath empty space, dark matter weaving galaxies together, we've only glimpsed the opening act. Consider how much remains hidden in plain sight. Dark energy pushes the universe apart while dark matter pulls it together, yet we still don't know what either truly is. Quantum foam churns beneath our feet, hinting that reality might be pixelated at scales we can't yet measure. Even time, once thought to be an unchanging river, bends and twists in ways that defy intuition. Every answer we find, like the Higgs boson confirming mass isn't inherent but borrowed from an invisible field, unlocks 10 new questions. It's as if the universe is a puzzle designed to keep us forever curious, forever reaching. What's next in this grand exploration? Perhaps we'll detect the faint vibrations of cosmic strings, relics from the universe's birth, humming in the void. Maybe we'll finally capture a neutrino's full story, tracing it back to a supernova or colliding neutron stars. Or imagine peering into a black hole's shadow and glimpsing hints of a holographic universe, where all we see is just a projection of deeper, simpler laws. The tools we're building, from gravitational wave observatories to quantum computers, aren't just instruments. They're passports to realms we've yet to imagine. But here's the most beautiful part. You're not just a spectator in this cosmic dance. The iron in your blood, the calcium in your bones, the very electricity firing in your brain, they were forged in stellar furnaces and scattered across space by explosions older than Earth itself. When you look up at the night sky, you're not just seeing distant lights. You're seeing the echoes of your own origins, the steps of a dance that began 13.8 billion years ago and continues in every heartbeat, every thought, every discovery. So what do you think lies beyond the next horizon? Could dark energy someday tear spacetime apart, or will we find a way to harmonize with it? Might quantum entanglement reveal a universe far more connected than we ever dreamed? The stage is set, the music is playing, and the universe is waiting for us to take the next step. Drop your boldest theories in the comments, because the greatest discoveries often start with a wild idea. And if you've enjoyed this journey through the cosmos, hit subscribe so you never miss an adventure into the unknown. After all, the dance never ends. It just finds new rhythms, new partners, and new mysteries to unravel.